Right, so this is 2.6, halogenoalkanes. Okay, so halogenoalkanes are alkanes, so carbon and hydrogen bonding, hydrocarbons, no double bonds, that contain a halogen. So a halogen is group 7, mainly chlorine, bromine and iodine. Okay, so it says here that one or more hydrogen atom is replaced with a halogen. Okay, their general formula is CnH2n plus 1, and then the X stands for the halogen. Okay, they contain carbon to halogen bonds, carbon to carbon bonds, and carbon to hydrogen bonds. Okay, they're quite polar because the carbon's quite positive and then the halogen's negative, so they've got quite a polar formation. Okay, they quite easily form dipoles, which means that they're quite easy to be subject to nucleophilic attack. Okay, so an attack by a nucleophile. Testing for halogens then, so you need to know the test for halogens. The top one is what we did at GCSE in year 10. So adding silver nitrate, chlorine gives you a white precipitate and it forms silver chlorides, bromine, cream, iodine, yellow. Okay, you can then also add dilute NH3, so dilute ammonia. No precipitate will dissolve and then there'll be no change with these two, so they'll just have the precipitate there if you add chlorine, and then you can do it with concentrated ammonia as well, and precipitate will dissolve for chlorine, bromine, and then there'll be no change of iodine. So it's just like a little bit of an overview about what they look like in terms of their structure. I'll just draw one out as well. Okay, so then that would be meth, so that'd be bromo, ethane. Okay, so moving on then. So halogens, we learned in the last time that how halogens form, so you can make them from alkanes or alkenes. Alkanes is free radical substitution, and then alkenes is an electrophilic substitution. So looking at this then, so elimination reactions, when a halogen is mixed with hydroxide ions, normally coming from NaOH, so sodium hydroxide, and heated at high temperature under alcoholic conditions, elimination occurs. In this reaction, a hydroxide ion, the nucleophile, acts as a base and accepts a proton, removing the hydrogen from the molecule. Okay, this results in the elimination of a halide and producing a carbon double bond. So this is how we go from halogenoalkanes back to an alkene. Okay, so you've got your nucleophile here, hydroxide ion. It acts as a proton and removes this H here. Okay, then because there's no bond left here, that bond moves and forms a double bond. The double bond then will force out the bromine, and that's what you end up with if you're going from a halogenoalkane to an alkene. Okay, big thing for us then is the formation of alcohols. So halogens contain polar bonds. As halogens, they're more electronegative. Okay, so they're more electronegative. We talked about this a bit at the beginning. So that means there's an electrodensity drawn towards the halogen. Okay, so they're quite good at nucleophilic substitution. The nucleophile, in this case again, OH, attacks the carbon by here. Same kind of thing again. The carbon then forces the Cl out. Okay, and you end up with an alcohol, no extra carbons. So this would be methanol and a free chlorine atom. So a big thing with halogens is all their uses. Before I move on to the uses, just want to mention that this is reflux by here. Okay, so you need to reflux it, and as well as being electronegative, they have different bond strengths. So carbon chlorine is the strongest bond. Okay, so it will undergo reactions slower because it's a stronger bond. Okay, so we talk about like hydrolysis and stuff, so the iodine carbon bond will undergo that faster because it's a weaker bond. Okay, and we can kind of look at that in terms of what happens when you add silver nitrate. You can see that one will actually react quicker. Okay, moving on to the uses then. These are the kind of uses that you need to know. Okay, so halogenoalkanes are used an awful lot as solvents. Okay, so instead of water, okay, they're polar, which makes them easy to use. Okay, they're non-flammable, so there's quite a lot of uses there. Okay, tetrachloromethane is used quite widely. Okay, also used as anesthetics. Okay, quite often in the olden days they were used to like chloroform and stuff to knock people out. Obviously we have more different anesthetics now, but they have got a use as anesthetics. also as refrigerants, so using them in your fridges, okay, because they're non-toxic and non-polar, and they're not flammable, okay. The big problem with them is CFCs, okay. So that used to be what we'd use in our fridges because it can change from a liquid to a gas in terms of removing the heat to make our fridges cool, okay? However, CFCs can go into our ozone layer now, okay? And that damages the ozone layer, which means that more UV rays can get in.